Okay, so good morning to everyone. Now, in yesterday's class, in the last class, sorry, not yesterday. So, in the last class, we have discussed about the Vliw processor and what will be the typical Vliw instruction format. We have already discussed. Now, we will continue about that how in the sequential processor the instructions are executed and what are the changes that is done in the Vliw processor, that how the instruction will be executed. We will see that first. So in Vliw processor, compiler is responsible for static scheduling of the instruction. That is, the compiler finds out which operations can be executed in parallel in the program. That is, already we have discussed that in our typical Vliw processor, there will be an identical operations present. So all of the identical operations will be present there, and we group together this identical operation. So all of these identical operations are we grouped together. So there will be inside this instruction, there will be multiple independent operation present, and we group together to make this instruction format. Okay, and that's why these instructions will be executed. The instructions will be executed in parallel in the program. Then compiler group together these operations in the single instruction. So which is all these independent operations will be grouped together and it will form the very large instruction word. The instructions within the Vliw instruction are issued and executed in parallel. Since in Vliw processor, one Vliw instruction words encode multiple operations, which allows them to initiate it in a single clock cycle. Now, what it means that there will be multiple independent operation present. So we have multiple, let's say in this instruction format, Vliw instruction formats, we have 4 independent operation. So the example which we have taken previously, we are doing that, taking that example. That is, here if you see, this is the example we have taken, that add R1, R2. This is an independent operation. Now what this operation performs, that the data that is stored into the R1 and the data that is stored into the R2, we are adding that 2 values. This is the another independent operation, that subtraction, that the value that is stored in the R5 and the value that is stored in the register 6, we are subtracting that 2 values. And this is what, this is the operation, independent operation. This is load R7 comma data. That means the data will be loaded into the register R7. This is another independent operation. And store R8 comma data. So that means the register, in the register the data is present. The register R8, the data is present, will be loaded here. So this is what, this is the 4 independent operation. And completely total of this 4 independent operation, we can say this as the Vliw instruction, that in here the independent operations are present, and what we do, this independent operation we group together. Now this independent operation are grouped together to form this Vliw instruction. So that means in one clock cycle, that means in a single clock cycle, this all independent operations will be executed because they are inside a same instruction word. That means all of these 4 independent operations will be executed in a single clock cycle. So that is the thing mentioned, that in here in Vliw instruction we executed, in Vliw instruction we executed or initiated this, that in a single clock cycle all of these independent operations will be executed. Then Vliw instruction contains operands and the operation to be performed by various functional units. Now we have seen that for addition we require what? Arithmetic logic unit of the CPU. Subtraction, for subtraction also we require the arithmetic logic unit of the CPU. Then for the load, Load instruction for load and store. We require what? For the load and store, we require the another resource, load store resource. That means it will be related to the memory. So that means here all are different resource we require. Since different requires resource we have required, and that means this will be different functional units. We have different functional units present, and these various functional units contains what? Operands and operation. That means in the add R4 comma R5, which we have seen here, R5 and R4 and R5. What is that? It is the operands. The operands are present, and opcode will be what? The add that is mentioned. This is the opcode. That means opcode is what? Over the operands, which operation should be performed, that defines this opcode. And the operands is the variable that we can say over which the opcode should perform. That means operation should be performed over whom? That is the operands. So Vliw instruction contains this operands and operation to be performed in various functional units. Now in this example if we take this example, then we will see that here for that ALU is used, but for load and store we require the memory resources for load and store. So that means ALU, arithmetic logic unit, a functional unit, then load or store memory, this is another resource. So different functional units, there is the different functional units present. So this point mentioned that Vliw instruction contains the operands and operation to be performed by various functional units. Okay, then one Vliw instruction encode at least one operation for each execution unit of the device. So length of the instruction increases with the number of execution unit. Now, if we increase the number of execution unit, then the length of the instruction will be what? The length of the instructions will be increased. Now, Vliw instruction, these Vliw instructions are usually at least 64 bits wide, 2 and 1024 bits wider in some architecture. So from here we can say that Vliw instruction, it is usually at least 64 bytes and maximum up to what? Maximum up to 1024 bits wider. In some architecture it may require. So this is the length. This is the length of the Vliw instruction. Now we will see the comparison of this instruction level parallelism on the sequential processor and the Vliw processor. So in instruction level parallelism, we will see how the sequential processor will work to execute this instruction level parallelism, and how this will be by Vliw processor, how it will be done with the Vliw processor. Hepzibah, please mute yourself. Hepzibah, please
Sorry,
mute
sir.
yourself.
Yes, sir.
Okay. Now, let's say, assume that the Vliw processor had two load and store units, one multiply unit and one addition unit. So Vliw processor has, we are saying that this Vliw processor has four functional unit present. That is, we are taking an example like that. Let's say that in this Vliw processor, we have two load store unit, one multiply unit and one addition unit. Four functional units are present. And let's say this is our instruction. This is our instruction, z equal to ax1 plus bx2 plus cx3. So this is our instruction. Now that means this instruction should be computed. Now we will see how this instructions will be executed in the sequential processor and how these instructions will be executed on the Vliw processor. Now this difference we will see here, that how this can be performed. So let's say first this instruction which is written ax1 plus bx2 plus cx3, this instruction, if it is executed in the sequential processor. So first, what thing we have to do? First, in the first clock cycle, we have to load the A. We have to load the A. That means we have to load this A first. Then after this, in the second clock cycle, we have to load the X1. So that is done in the second clock cycle. We have to load this X1 in the next clock cycle. Now after this, what we will do? This we have already loaded A and X1. Now between them, multiply we are doing. So after multiplying it, let's say we are storing it into the value Y1. So that means in the third clock cycle, what we will perform? We will perform the multiplication between A and X1 and we will store it into the Y1. This is what in the third clock cycle we will do. So that means AX1 have been done. After that, same as that for BX2 we will do. That means first in the fourth clock cycle we will load B, then fifth clock cycle we will load X2, and in the sixth clock cycle, let's say we are storing this multiplication or the result of this product into the Y2. So in the sixth clock cycle we will write multiply Y2 comma B comma X2. That means multiplication between them will store into the Y2. Okay, so now after this, we get the total product value of Y1 and Y2. So that means in the seventh clock cycle, what we will do? In the seventh clock cycle, we will add this two values Y1 and Y2, and let's say we will store it into the Y3. So adding these two values, because AX1 plus BX2, so that means what the final product we get? Y1. That means this value is stored into the Y1 and this BX2 value is stored into the Y2. So that means addition of this two will store it into the, let's say we are assuming we are storing into the Y3. So that means what operation we will write there? Add Y3 comma Y1 comma Y2. That means adding of this two, the value that is stored into Y1 and Y2, we are storing that value into the Y3. After adding, we are storing that value into the Y3. So this is the in seventh clock cycle we have performed that. After that, we will have to in the 8th clock cycle we will load the C. Then in the 9th clock cycle we will load the X3. Then after loading that, in the 10th clock cycle, what we will do? We in the 10th clock cycle we will do what? That adding multiply these two values, we will, let's say we will store it into the Y1 again. We will store into the Y1 again. And after that, in the 11th clock cycle, what we are doing? That the final product which we got, this final product plus Y1, and we are storing that value into the Z. So that means execution of this total instruction. If we see this total instruction, we require 11 clock cycle. That if we perform it into the sequential processor. But in the Vliw processor, we will require less number of clock cycle. Now, why the less number of clock cycle will be required? Because in Vliw processor, we have seen that independent operation. The independent operation we group together and there is multiple functional units present. So in a single clock cycle, the instruction can be executed. So you see load A and load X1. These two are performing where? Load and store. That means over memory are they are performing. So that's why we have do what? We have used it into the one clock cycle. Then the next instruction, you see in the next instruction what we do? Load B and load X2. So in the next instruction, load B and load X2, we are done, and with this also we have done multiply Y1 comma AX1, A comma X1. That means after this here we have also performing that multiplication. The multiplication we are performing between A and X1 and we are storing that value into the Y1. So in the next clock cycle, we are doing that. In the next clock cycle, this three operation we are performing. Now there will be no problem because there is what? We have in the Vliw architecture, or the Vliw processor architecture, what is there? There is multiple operations can be present, and inside it multiple our functional units are there. So that means what will perform? We will perform this into the single clock cycle. There will be no problem. So that's why we perform all of this operation in the clock cycle 2. Then in the clock cycle 3, what we do? In the clock cycle 3, we have done loading this C and loading this X3. And after that, this multiplication of BX2, we are performing in the third clock cycle. So that means what? If we see that up till now we have required what? We have required 9 clock cycle for that. But inside, you see, inside this 3 clock cycle, we have performed all of this operation. We have performed all of this operation in the Vliw processor. And in the clock cycle 4, the total addition of y1 and y2 means ax1 plus bx2. We are getting the final product and we are storing it into the y3. And the other third operation, that is cx3. This cx3 we are loading into the y1 again. So that means in this clock cycle 4, we have performed that. And in the clock cycle 5, the total final operation, that means in the Z, we are storing the final operation. So the final operation after performing that, we are storing into the Z. So that means you see only 5 clock cycle we require. Only 5 clock cycle we require to execute that instruction. Whereas in the sequential processor, we require the 11 clock cycle. So which we will do? We will obviously use in the Vliw processor, because in less number of time, we able to execute the instruction parallelly. We able to execute instruction parallelly. So that's why the Vliw processor is used. So this is the advantage. We say that we require less number of clock cycle, and this less number of clock cycle, our instructions get executed, then that instruction executed in the sequential processor. Okay, clear till now? It is clear to everyone till now?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay. So now we will move to the advantage of the Vliw. So advantage of Vliw processor is dependencies are determined by the compiler and used to schedule according to the functional units. So which type of a functional unit should require for this operation? This will be determined by the compiler, and this will be scheduled according to the functional units. That means if addition we require, let's say our in this total Vliw instruction format, there is an instruction, let's say in that instruction we require the addition. So for this addition, which type of a functional units we require? The CPU will be for the arithmetic logic unit of the CPU will work. So we require that. So that is which functional units we require to execute that particular independent instruction. This will be determined by the compiler. This is the advantage. And by seeing that it should be scheduled, that means which it will require, which operational to perform this operation, which functional units are required. This will be determined by the compiler. So that's why the dependencies are determined by this compiler. And it is also, the advantage is here also that it is reduces the hardware complexity. Now till now, which processors we have seen that number of cable connection, let's say number of cable connection get increased, or we say that number of intercontrol logic get increased. So that is what, if we use the Vliw, we do not have to such headaches there, and hardware complexity will be what? It will be reduces. That means what? Tasks such as decoding, data dependency detection, instruction issues, etc. becomes simple and ensures low power consumption. So this is the advantage of the Vliw instruction. But each and everything has disadvantage also. because that disadvantage is higher complexity of the compiler. Now compiler should be complex because what? The instruction, VLW instruction length is what? We have seen that it will be 64 bits wide to the 1024 bits wide. That means instruction is very large. Now to compile that instruction, to execute that instruction, we have to require a much more complex compiler for that. So the system which it uses the VLW instruction will require high complexity of the compiler. Complex compiler is required to execute such a long instruction, because VLW means what? Very large instruction word. So that means executing for this type of instruction, we require less complex compiler, because in normal compiler with such a large volume of instruction, it cannot be executed. So we require our complex compiler. Higher complexity of the compiler is required. So now this is also a cost related thing, that if we use that, that means cost will be increased. So same problem now this happening for this. And also VLW processor cannot react on the dynamic events. So if any dynamic events came, VLW processor cannot react on that particular case. So these two are the disadvantage of the VLW processor. And where this Vliw processor are used, the applications like digital signal processing or processing of media data like compression or decompression of the image and speech data. So now with compression and decompression of image and speech data, that is a very large volume data. So in that case, or digital signal processing, in that case, this is where large data should require, large volume of data should be required. So in that application, in that cases application, we require this Vliw processor. Now the Vliw processor, basically some Vliw known process is Vliw mini supercomputers, that is multi-4 trace, 700 by 300, 14 by 300, 28 by 300. These are the supercomputers. These are, in your normal system you will not see that it will use the Vliw processor. Now which of our normal system there is present? We do not have Vliw processor in that, because we do not require such a large amount of data. So why we will do in the normal, for our normal function, Vliw processor? So the systems we use, like the PC or the system you have that doesn't have the Vliw processor. Vliw processor only requires when we have the large volume of data like this, like means large volume, 1 GB, 2 GB, tetrabyte, we can say that large volume. So in that cases what? In that cases this type of system is required. So that's why it is a supercomputer. When this supercomputer, in this supercomputer's Vliw processor is used, and this known supercomputers in which the Vliw processor is used are the multi-fold flow trace, 700 by 300, 14 by 300, 28 by 300, etc. And other example is single chip Vliw processor like Philips Life chips, DSP processor. In that cases, this Vliw processor is required. So very thing you note that Vliw processor is basically to execute large number of instruction, large number of instruction, or the volume of the instruction is large. Then we do what? The multiple independent operations or the instruction we group together. So why? To large volume of data execution, we require less clock cycle. So that's why we use the Vliw processor. So these things you should keep in mind. So this is all about our Vliw processor. Now today we will see another processor, that is vector processing. that is the vector processing. Now, vector processing is basically what? If there is a class of computational problems, means large number of calculations we require. Sometimes it required large number of calculation. In that case, this large number of calculation is beyond the capability of the conventional computer. So it is beyond the capability of our normal conventional computer. Now, to solve this such a problem, we require vast number of computation or vast number of calculation. Then if we perform it into our normal computer, this large number of calculation or the large number of computations, then it will require a day or even a week to complete. But computers with vector processing are able to handle such instruction. The computers which use the vector processing has ability to handle such instruction, and they have application in the following fields. Now, long range weather forecasting, that you see that sometimes it is shown that in 30 days weather calculation, 1 year weather calculation. So that means what? This type of large, in this calculation, now long range weather forecasting we require the calculation part. So let's say sometimes it is shown that next 30 days, what will be the weather forecast? Now that means what? We require calculations, because without calculating we cannot know that what will be the next 30 days weather forecast. So that means this, for this large volume or large calculations, that means in this 30 days calculation, to know that large complex calculation if we have, then the system which uses vector processing will able to handle that such instruction. We perform in our normal computer also. Okay, we are able to perform that in normal computer also. But if we go to perform it into the normal computer, then a day or a week can be required, because our processing power, the processor which we, in our system it is used, has not so much processing power. So that's why this is the problem. And if such required, then the system with vector processing is what it is used, because it will able to handle that such instructions very efficiently. Now, this is an example. Let petroleum exploration, medical diagnosis, aerodynamics, and space simulation. Now, if you see any space simulation, then you will see that how much calculation it is required. Large calculation is required for that. And this is not done in our normal system. They have some supercomputers present, and there that supercomputer uses this our vector processing. So like this, the vector processing is done. And another is the artificial intelligence of an expert system. For image processing, we require that. Now, complex instruction which is done on the multiple data at the same time. That means here the instruction is what? This complex instruction, and the operation we perform on the multiple data. With this calculation we perform on multiple data at the same time. And so for that we require a better way of instruction execution, because we have many calculations, and this many calculations we are performing in the multiple data and in the same time. So that means what? That means for that we have required a better way of instruction execution. And this better way of execution will only be achieved by vector processing. Now, simple words, we can say SIMD, instruction is single, but we are performing over that in the multiple data. SIMD says that single instruction, multiple data. So instruction is single, but we are performing over into the multiple data at the same time. So this is what that in our vector processing works. And vector processing not only use the instruction pipeline, that the pipelining is what we have seen, that pipelining in what we have divided the program, and this program has total 8 instruction. The example which we have taken, that in that we have 8 instruction, so that 8 instruction is done parallelly, it is executed like that in the pipeline we have seen. But it not only vector processing not only work over the instruction pipeline, it also works on the data, and it is what multiple data, over multiple data it is working and in the same time. And in computing, a vector processor is a CPU that implements an instruction set containing instruction that operate on one-dimensional array of data. It operates on the one-dimensional array of data called the vectors. And compared to the scalar processor, if we compare the vector processing with the scalar processing, for scalar processing, instruction operate on the single data item, means it operates on the single data item, but vector processing instruction works on the multiple data item. This is the difference between the vector processing and the scalar processing. And vector processor have high level of operations. Vector processor has high level of operations that work on the linear arrays of numbers or vectors. So this is the diagram we see, that from here the scalar quantity, that means instructions will work over a single data, but in vector quantity is what, the single instruction will work on the multiple data. So here single data it's working, but in this here you see that this single instruction, if we say it is working on the 4 data. So this is the scalar processor and the difference between the vector processing. And vector operation is what, vector operation, let's say we will take this example in the vector here. Now same as that, if let's say we have to add the values, let's say we have to add the values here. Now addition of two values in the two arrays. Now our problem is addition of the values in two arrays. Now if we write in the C program, then what we'll write, that means two arrays we will take, and total 3 array we will take. That let's say this is A10, B10 and C10. These are A, B, C are the 3 array which is of integer type and has storing of 10 data. That means this array has a size of 10. So all of this array has size 10. Then we use the for loop, and in this for loop we will do what? We will, inside this for loop we perform Ci equal to Ai plus Bi, and after that, that means we will perform this total execution like this. If we want to add two arrays in the C, if we do that, we will perform like this. But if we done in the assembly language, then what we have to write, like this, initialize I equal to 0, then read AI and read BI. So to read arrays we have to read, and then we will write store CI equal to AI plus BI. This means that AI and BI two arrays will be added, and it will be stored into the CI. Then increment I equal to I plus 1. That means increment will be performed, and how many times it will be done? I less than 10, because 0 to 10 it will work. So 0 to 9, because we have 10 elements there, and we will continue. So this is the code. If we write into the assembly language, if we write this into the assembly language, now vector processing has ability to remove overhead instruction fetch and execution of in loop. That means instruction fetch and execution, this we do not done in the vector processing. This is not required. But then how this instruction will look like? How this instruction will look like in the vector processing? The instruction will simply write like that in vector processing. That instruction can be written as C 1 to 10 equal to A 1:10 plus B 1:10. So this is what we'll only write this single simple statement. Then this total, this in C, what we have seen in the assembly language, that means here also in this single instruction like this, we will totally perform our execution of what we want to execute. But if we write into the C, then this, how many codes should be written? In the assembly language, you see we have to write like this, but in the vector processing, we will write a simple vector instruction that C 1:10, A 1:10 plus B 1:10. This will simply tells that we are taking an array which is of this 1:10 suggests that it has the size 10. This B array has size 10, and addition of these two, the result will be stored into the C array, which is also the size of 10. Okay, so only simply writing this instruction, we will able to, simple instruction, we will able to execute that. What this total code are executing, this are done in this single instruction. Okay, clear? It is clear
Yes,
to
sir.
everyone?
Yes, sir.
So this is what in the vector processing we done. And the thing that a vector processing, we say of any vector instruction, is look like this. That means there will be an operation code, a base address of the source 1, base address of the source 2, base address of the destination, and a vector length. So a simple example is, first this will be total length of a vector instruction. That